All right. Let's just move on. Okay. So we've been talking about lensing surveys, current surveys, future surveys. Okay, covering imaging over large areas of the sky. One thing that all these surveys will do is to find lots of massive clusters. So we heard from Howard and from Mike, I guess both of whom are not here, about the RCS2 survey, for example. And so they've been finding lots of very massive clusters at high redshifts. So an example is shown here. This is working. So this is a redshift 0.7 cluster. The mass estimates are still rough, but roughly speaking, the mass seems to come out around a few 10 to the 15 solar masses. Okay, like sidereal mass. Okay. All right. So that mass at that redshift corresponds to a roughly 6 sigma or 7 sigma fluctuation. Okay. Now, as you probably know, 7 sigma fluctuations, should be rare. Okay. So the first question, the first question that occurs to you, what's the first thing that you think of after seeing this object? Okay. Is whether or not the detection of this object in the RCS volume is consistent with our cosmology. Okay. The first thing that you think of. Right. So that question, currently cannot be answered. Okay. Simply because the mass function out at 7 sigma isn't known. Okay. So the reason for that is very simple. The reason for that is that our current calculations of the mass function, okay, they're all based on simulations. Okay, they're all purely numerical. And so because simulations have a finite dynamic range, there's a finite range of masses up to which we can calculate the mass function. So the current generation of simulations that can run so far, like the Millennium Run and many larger runs, okay, they've achieved a calculation of the mass function out to around sort of 4 sigma masses. Okay, that's very impressive, of course, right? But it's nowhere near the 6 sigma, 7 sigma, 8 sigma objects being found even currently, let alone future surveys. That'll let alone future surveys, like DES and BOSS and so on. Okay. So if we want to calculate the mass function over the mass range probed by these surveys, okay, simulations won't be good enough. We'll have to use a more sort of theoretical approach. And one sort of aside I want to make, is that fitting formulae are not theory. Okay, So over the past decade, since like 99 or so, okay, lots and lots of fitting functions have been developed, to approximate the mass function measured in simulations. So because none of these functions, so because none of them, have a physical motivation, okay, none of them can be extrapolated beyond this mass range, okay. That's obvious, hopefully, to everyone. Okay. So if we want to go further, we can't use fitting functions, we can't use simulations, we have to start, real modeling, basically. Okay. So the first model that people, thought about, is the Press-Schechter model. Okay. This is a very simple, very well-known model.
Which one's the best?
I think it's pretty clear if you've met either one. Right. Okay, so the basic idea behind the Press-Schechter model is that the fraction of mass in collapsed objects, okay, above some given mass, the assumption is that that fraction of mass, in halos, is given by the fraction of the volume in the universe for which the local smooth density exceeds a critical threshold for collapse, delta C. And the value for delta C is calculated using the spherical collapse model. Okay. Press-Schechter, is a qualitatively nice way of thinking about halo formation, but in detail, it fails very miserably, especially at high masses. Okay, so for high mass halos, the Press-Schechter mass function, falls below the actual mass function by factors of even up to 10. Okay. So there are lots of well-known problems with the Press-Schechter model, most of which, aren't really a big deal. But the following problem, however, so the following problem, well, so the following problem, well, for high mass halos, that can be very, very important, which I'll describe right now. Okay, so suppose that I'm plotting the smoothed linear density as a function of position in the neighborhood of some very high peak. Okay, and suppose that the smoothing scale is this sort of scale. Okay, and suppose that the height of the peak, okay, the peak height, okay, suppose that it happens to fall just above the threshold for collapse. Okay, so the spherical collapse model, therefore says that this region has collapsed. Okay, so how much mass? Okay, so how much mass has collapsed from this region? Okay, so the correct answer is that the entire region has collapsed. Okay, that is the result of the spherical collapse model. Press-Schechter, however, says something very different. Okay, so because Press-Schechter is making a local point-by-point comparison in space between the local smooth density and delta C, okay, because of that, Press-Schechter instead will say, that the volume that has collapsed just is this little small volume, okay, right? So this is obvious, right? Okay, so you can see that the Press-Schechter, sort of mass counting, okay, you can see that this grossly undercounts the amount of mass corresponding to this region, okay, and the problem gets worse and worse if the peak height, the problem gets worse and worse, if the height of the peak, barely exceeds the delta C, okay, and for rare peaks, like the 4 sigma, 3 sigma, 5 sigma peaks, okay, the peak heights will be just at threshold, just by definition. Yeah.
It looks like with the Press-Schechter thing, as the tip of your peak just gets over that threshold, that the mass will kind of start from zero and monotonically increase. Whereas if you're saying everything between those two thick bars collapse, and it almost looks like a step function.
Yeah, so as long as you're above threshold, yeah, that's right. That region has collapsed.
So I mean, it's kind of seems a little about this, but like this
okay.
step function.
Yeah, so it's a step function, for a given smoothing scale. If you consider a smaller smoothing scale, the peak, peak height will be above threshold. Okay, and so that's the way the mass sort of builds up. Okay. Yeah. Okay. So that's the main reason why the Press-Schechter mass function fails so badly at high masses. Okay. The issue is that Press-Schechter. Yeah, okay. Right. So the issue is that Press-Schechter does correctly find regions above threshold, but it does not correctly assign mass to those regions. Okay. So a better approach, clearly, okay, a better approach, other than this counting of mass, okay, well, a better approach would be, just to count peaks themselves directly. Okay. So the idea is that we associate one-to-one, halos with peaks of the initial density field. Okay, so for each halo, there's a peak corresponding to that halo. Okay. So to count the number of halos, then, all we do, all we have to do is to count the number of peaks. Okay. And fortunately, the problem, the problem of counting peaks is, is a solved problem. Okay. So back in the 80s, Bardeen, Bond, Kaiser, and Soleil worked out the statistics of the peaks of Gaussian random fields in gory detail. Okay. So in principle, therefore, this problem is a solved problem. Thanks to BBKS. The one final ingredient you need is to figure out which peaks make which halos. Okay. Right. So there are many possible ways to figure out the mapping between peaks and halos. Okay. And here at CITA, for example, we are currently working on a calculation that is ab initio. That's still in progress. But a easier way of to calculate this mapping between peaks and halos just is to measure it in a simulation. Okay. So let me show you what I mean. Okay. So so this is a plot. This is a plot of the heights of peaks that form halos in a simulation. Okay. So the x-axis is sigma of m. So high masses go towards the left. The y-axis is the Lagrangian, the linear density peak height. Okay, for the peaks making these halos. So you can see that for high mass halos, okay, over here, okay, you can see that going towards high masses, the peak heights converge rapidly to a value, around 1.7. Okay, the spherical collapse prediction. Okay, no big surprise, of course. Okay, because high mass halos collapse basically spherically. All right. So that was for a particular cosmology and power spectrum. If you varied the cosmology and power spectrum, not much really changes. Okay. So even for a lambda CDM simulation, okay, a redshift 0 when lambda is very large and stopping growth, not much really changes. Okay. The peak heights are still around 1.7 at high masses. There are some possibly interesting effects as you approach n of -3. But I probably won't get into that here. This is sort of technical. But if there are questions, I'd be happy.
I understand you found peaks of the present day and you've gone back and figured out what.
So you find halos. So you find halos at redshift 0, for example. Okay, right? You trace the particles back to the initial conditions. Lagrangian space, and you find the peaks. Of those areas. That have collapsed to form the halos. That's the idea. Okay. Okay, so those are the heights of the peaks that collapse to form halos. Next, I'll show you the shapes of the peaks that make halos. Okay, so that's shown here. So these are the stacked average Lagrangian profiles of the peaks that make halos. Okay, plotted as a function of here power spectrum slope, and here's a function of the peak height, the mass, basically. All right. So the main point to note here is that the shapes of the profiles. Okay, the shapes are basically similar to top hats. Okay, like in probability near 1, slightly smoothed by a small exponential smoothing. Okay, right. So the amount of the smoothing, the shape of also the smoothing length. Okay, you can see the smoothing length appears to be a weak simple function of the shape of the power spectrum, and also a weak simple function of the peak height.
A simple question. When you trace it back, right,
Mm-hmm.
on the particles that the height are redshift 0,
Right.
You look at the initial density field, these particles may be many peaks.
Exactly, in principle.
What do you mean by
So the filling factor you see here, okay, so the filling factor you can see here is 1, right, at small radius. So that isn't happening, okay?
You're
Right.
saying there is a one-to-one correspondence between peaks.
So contiguous regions are collapsing to form the halos, is what I'm saying.
What?
Contiguous regions are collapsing to form the halos at high masses. As you go towards lower and lower masses, the filling factors, fall slightly below 1 to around, say, 0.9 or so. Okay, possibly indicating, separate regions might be, merging together. But at high masses, it's just contiguous regions.
So this is the fraction of particles at each radius that end up in.
Exactly.
So that statement about lower masses sure to count for true. Yeah, that 90% of the masses are coming from a single peak. Those merge.
Yes, and right, and they merge, and they merge smoothly, right?
I can believe what you're saying for mu of 3.9.
Yeah. So even for a nu of like 0.4, okay, the filling factors are like 0.8, 0.9 at small radius. Dude. Okay, so how much do you want to bet?
Sorry?
So how much do you want to bet?
If I'm persuaded the simulation is a decent one, that
So we've done this for multiple simulations, yeah.
that was the way to address equality.
All right, fair point. Right. Right. But if it was a problem in the simulation, though, you might think that, let's say, tree codes versus, P3M codes might give different behavior, but they don't. Yeah. Right. Okay. So all right. Okay. Right. Okay. So we have now calculated, just numerically, empirically. Okay. We've calculated the shapes of the peaks and the heights of the peaks that form halos. Okay. So now it's a straightforward exercise to take these peak profiles and peak heights and to plug it into the BBKS machinery to calculate the number of these peaks. Okay. So let me show you how that looks. So yeah. So here are the results of doing that. Okay. So the blue curves here show the peak abundance you would calculate for these heights and these shapes. The black curves show the Warren et al. Mass function. This is one of the fitting formulae, calibrated simulations. Okay. They're all basically the same around here. Okay. Okay. So one point I want to emphasize is that these blue curves, okay, the peak abundance curves, okay, they have no freedom to be adjusted. Okay. Once you have specified which peaks you're counting, okay, the power spectrum fully specifies these curves. Okay, there are no parameters here. Okay, you have no way to move these curves around once you specify which peaks you want to count. Okay. So the agreement that we find, therefore, is encouraged. Okay.
Can you say a little bit? I still don't understand. When you say a peak, what smoothing scale are you using?
Yeah. So right. So we're smoothing on the mass scale of the halo. That's what you were looking for. Okay, the halo mass scale, and the filter is this. Okay.
It's almost a top.
It's very close to a top hat, especially at a large radius. But the small smoothing is important because the statistics of the curvature of the peak also matter for the abundance. And for a sharp top hat, the variance of the curvature diverges. Okay.
What do you put a curvature?
What's that?
What does a curvature mean?
Right. Okay. So a peak is defined as a place as a place where the density is a maximum, right? The first derivative vanishes and the curvature is negative, or negative. Well, this way. Right. Okay. Right. So the number of peaks, therefore depends upon the statistics of that curvature. Right. Okay. And that curvature depends upon how you have smoothed the density field. Okay. Right. So if you use a top hat, the variance of that curvature diverges, and you cannot calculate anything. Okay. So the smoothing actually does matter. Yeah. Any more? Okay. Okay. So once we have this formalism in place, we can do things besides just calculating the number of halos, the mass function. Okay. So let me show you some examples of that. Okay. So besides the mass function, we can also calculate the clustering of halos. Okay, the halo bias. So one example is shown here. This is a comparison of the halo bias you would calculate compared to values computed in a recent paper by Darren Reed for the clustering of very, very massive early objects. And it matches. No big surprise here, actually. Okay. But a more interesting test is to compare more subtle clustering properties. So, for example, the assembly bias you can also predict analytically. There's a comparison of the assembly bias you would expect. That's the solid curve compared to the assembly bias that you measure in a simulation. The curve has no freedom, of course, and it matches again. Okay. In a similar vein, so besides just counting the number of peaks of some given height, okay, you can also count the number of peaks of a given height in a given, say, curvature or a given slope or whatever. Okay, we expect those peak parameters, to determine the late time structure of the halo, like its concentration. Okay, so because we can predict the statistics of those peak properties, okay, it should be possible in principle, it should be possible in principle, to predict these, to predict the probability distribution, okay, like your halo properties like concentrations and so on, okay, analytically, and that's still in progress.
I mean, the kind of merger tree approach.
Mm-hmm.
Couldn't you have two identical peaks that at a later time have different merger history and then therefore lead to halos of different concentrations?
Yeah, so there will probably be noise between these peak parameters and the final and the final halo parameters. Yeah, we would expect. So the relation between the peak parameters and the final halo parameters, that probably has to be calibrated numerically.
Are you getting higher or lower than Warren and I couldn't distinguish the color.
Yeah, so the mass function is not universal. Okay, so it's a function of the shape of the power spectrum. So for example, so at high masses, like in 10 to the 15 solar masses, roughly speaking, let's say, we get somewhat lower abundance than Warren et al. In contrast, as you approach sort of -3, we get slightly higher. Okay, and this comes from the shape of the power spectrum dependence. It comes from the peak height dependence on the power spectrum.
Did you get the sense of the scatter from this mass function?
So scatter, what do you mean?
For one generalization.
So we're computing. So we're computing the number of halos, the mean number in the universe, right? Well, so the mass function, is the mean number. Yeah, right. Yeah. So the bias gives you the scatter in a sense, yeah. Well, in a loose sense. Okay, right, okay, so yeah, concentrations and so on, okay. We can also apply the same sort of reasoning, to models besides just, like, standard sort of vanilla Gaussian field and the CDM. So we can, we can do things, like modified gravity, for example. We can also apply the same sort of reasoning for models with a non-zero primordial non-Gaussianity. So let me just show you one final plot of that. So if you apply the same reasoning, okay, to the properties of the peaks that form in these sort of models, you can show very easily, so very easily you can show that the clustering of the halos, the bias of the halos takes on a particular scale dependence, of this form. And if you numerically calculate in the simulation the clustering of the halos you find, it matches it basically perfectly. And so Chris will, I think, be talking about very similar things in this talk. Okay, right. So let me close where I started. Just by mentioning this is a very massive object, okay, found in RCS2, 6 sigma, 7 sigma fluctuation, okay. So because we think we now have, a mass function, okay, we can estimate the likelihood of seeing something this massive in the RCS volume, and that number comes out at around 10 to the minus 4 level, okay. So therefore, the likelihood of our cosmology, given the detection of this object in the RCS volume, would strictly speaking be around that. And so on that happy note, I'll stop.
What did you assume about the mass profile of that one object? So you have to decide where the Einstein radius is going to be.
Yeah. Okay. So Mike has strong lensing. I also have weak lensing, X-ray, SZ, velocity dispersion masses. So the weak lensing mass, the M200 for that is around a few 10 to 15. Yeah.
What did you find your mass functions for this kind of, or what would be the probability with wiring?
Yeah, it's actually pretty close. It's like a factor of a few times higher, maybe. So I was hoping that would be the reverse. I was hoping that this would come out much higher, but.
So on.
I think the truth is much higher than water. Much higher, maybe not, I don't know. It's not going to be a factor.
Why?
Okay, so you've spoken with God and you've figured out. I'm sorry.
No, because those simulations the way they did the fields is when they look at high mass halos, they started their simulations too late.
Right.
And because of transients, the mass function gets suppressed in high mass. So I don't know whether it is will make this comfortable or not. Definitely will go in that direction.
Yeah, by some small factor, right? Yeah.
Presumably, the really high mass end, the cloud and cloud problem
Is negligible.
absent. So
Yeah.
you should be able to recover what the peaks theories should give you. Do you find that or not?
This was the peaks theory, yeah.
Yeah, but if you compare with what would be predicted from BBKS and so on.
This is BBKS, yeah.
Okay.
It's just not a top hat.
It's just not a top hat, yeah.
Okay, maybe let's talk about it afterwards. Maybe I missed something.
Oh, yeah, for this object. Yeah, so, yes. So that arc has a redshift of 3. So the strong lensing mass, is the mass inside of that radius for that lens redshift, and that's what's redshift.
Inside has a bunch of galaxy groups, redshift 1.5, 1,
Right.
3.
That's right. Yeah, okay. So this mass is M15,000, okay?
Sorry?
The mass inside this radius, that mass is so the density inside of that radius is 15,000. So you can have like filaments or whatever you want. It's not going to change this. It's not going to change that number. Oh, what's that?
I mean, we have one of these in the bullet clusters that we have this nice curved object, looks like high redshift. It's 2 arc minutes, only
So there are lots and lots of different like arc features there, and weak lensing, and X-ray, and SED, and velocity dispersion. This is quite clearly a
But
lens.
your conclusion is sensitive to the redshift that you're putting in this mask.
Uh,
Final effect is -4 depends on the
that is correct. And again, we have, well, not we, I mean Mike and Howard have all these different independent mass estimators. Velocity dispersion is independent of stuff as redshift 1. The X-ray is not affected by any of that, I guess, right? They all come out consistent to each other. Yeah, so too bad Mike, took off so he could tell us more about this object, and why they haven't published it yet, despite having all this data for n number of years and months. But
So, if you wanted to change your 10 to the -4 to 10 to the -1.5, what's the mass have to be?
yeah, so right. So the power spectrum on these scales, the slope is close to sort of -1 or something. Okay, so sigma is varying very rapidly with mass. Okay, so if you lower the mass by a factor of like a few, you're totally fine.
So 1 10 to the -15.
Then you're totally fine. Well, like for example, like MS 1054, I guess. I mean, I think that's the number. Its mass is comparable to this at redshift like 1. I mean, I'm not this. I mean, like its mass is comparable to 10 to the 15 at redshift 1, and it's totally fine with our cosmology. Okay, so it's because it's because sigma varies so rapidly with mass in this sort of regime. That's the origin of the problem. Okay, right. So if we could lower all these 4 independent mass estimators, separately by a factor of a few, we're golden.
But you put a factor of 2 practically in the estimate.
Yeah, no, that's right.
So you say that it's
What's that?
If I claim that mass function is not a warrant, so if you shift it a little bit because it's decaying exponentially so fast, then you should probably.
Yeah, Mike, go on.
which cosmological parameter is the mass function at this very high end most sensitive to? If you wanted to believe this,
Sigma 8, right?
So to make it how high do you have to push sigma 8 to make this?
Yeah, so even if you use the old concordance cosmology with like a sigma 8 of 0.9 and omega matter of 0.3, the probability is still like 10 to the -3.
So you need to push sigma 8 up to like
And
1.
maybe like 1, yeah.
Is there any non-standard cosmological parameter that might get the job done? Or
Also, right, like FNL in principle could do this, but the values you would need are ruled out already by Chris's work. So, which he'll tell us about, I guess, later on today. Yeah. So hopefully the answer just is that Mike et al. Have overestimated the mass.
Maybe that's why they're not here.
Bit passing here, yeah.
And what's the lowest mass range you can apply for your formalism?
So I'd expect this to be okay down to around 3 sigma. Numerically, you find that it matches like down to 2 sigma. I don't see any reason why that should be the
2
case.
sigma is like 10 to the
Yeah, so 2 sigma I guess today is I guess like between 10 to 13, 10 to 14, somewhere around there. I wouldn't expect it to be valid down there though.
then it's more complicated,
Right. Yeah, right. Clouds inside of clouds. Yeah. So.
Thanks.
Okay.
Any last question? All right, so thanks, Neal, again.